You are sitting at your keyboard, right? Like deep in a terminal session.
Oh, yeah. Totally in the zone.
Right. And your muscle memory is just completely taking over. You type out the first half of a command, followed by maybe the first 3 letters of a target file, and you hit the TB key.
Right. You don't even think about it.
Exactly. You don't even think about it. You just expect the system to, interpret your intent, read the directory, and instantly finish the file name. But instead, the cursor just blinks at you.
Yeah, just staring right back at you.
It's infuriating. So you hit it again, nothing. And just like that, the flow state shatters. You're left staring at this stubbornly incomplete string of text, and you're forced to manually type out the rest of the path like it's 1985 or something.
It really is a wildly disproportionate frustration, isn't it?
Oh, absolutely. It's this sudden mechanical friction of a failed autocomplete right when you are operating at the speed of thought, like repeatedly pushing a broken crosswalk button. Just this blind hope that one more tap will suddenly make the system understand what you want.
That's a great way to put it. And that friction is exactly what happens when the invisible contract between the user and the command line interface just breaks down.
Right.
Because we've been conditioned by decades of a mature tooling to treat the TA key not as a character input, but as an active query to the system environment. So when a tool fails to respond to that query, you are instantly yanked out of your workflow. You're reminded that you are, in fact, interacting with a rigid piece of software that lacks basic environmental awareness.
Okay, let's unpack this. Our mission today for this deep dive is to explore how a seemingly tiny, frustrating UI issue in a console app led this developer to a specific code fix and ultimately a much broader philosophy on software design.
I love this topic because it perfectly illustrates the hidden mechanics of the tools we use every day.
It really does. So we are pulling from an excerpt by a developer named Ang, and it's specifically titled Notes on Haskell Programming, Part 143, published on May 23, 2026.
And we should note, Ang isn't just complaining about a broken tool here.
No, not at all. Ang is the developer actually building the tool. It's this console application called XS2ebook. And during development and testing, Ang noticed this glaring flaw. No matter how many times they pressed the tab key, the app absolutely refused to autocomplete the input txt file name.
Right, and what's fascinating here is how Ang's frustration immediately pivoted into an investigation to solve the problem. Because in a console application, autocompletion isn't just some luxury, It's the primary way users navigate.
Yeah, if it's broken, the app feels broken. But identifying the problem is only half the battle. To fix it, Ang had to look really closely at the library powering the app, which leads us to this very specific Haskell solution.
Yeah, and building a CLI tool often lulls developers into this false sense of simplicity. You just assume that because the interface is text, the operating environment will handle the input parsing for you natively.
Right, you think it's just going to magically work.
Exactly. But Ang's X2book application highlights a really critical gap. The operating system's shell has no intrinsic knowledge of what your custom binary does. It doesn't know what flags it accepts or what specific file types it needs as arguments.
Because the shell is totally blind to the internal logic of your application, right?
Precisely. Unless you explicitly wire up a communication channel between the two.
But wait, here's where it gets really interesting, because I have to push back on that idea of a false sense of simplicity just a bit.
Oh, how so?
Well, if I'm writing a modern application, shouldn't standard libraries kind of abstract that communication channel away? I mean, we aren't writing raw assembly here. Ang is writing this app in Haskell using a dedicated library for argument parsing called optparse-applicative.
Right.
So if you are importing a library specifically designed to handle command line arguments, it feels counterintuitive that autocomplete wouldn't just be an out-of-the-box default. Like, if the code change is brief, why wasn't it just working by default? Is it normal for developers to have to hunt down the specific syntax to get a basic function to work?
That is the perfect question. And it cuts straight to the underlying philosophy of Haskell. And strictly typed functional programming in general, honestly.
Okay, so it's a feature, not a bug.
In a way, yeah. Haskell actively resists implicit magic. It demands explicit, mathematically sound definitions for every single operation. So to understand why optparse-applicative doesn't just guess how to autocomplete, we have to look at the specific mechanism of the library.
Which is applicative parsing, right?
Exactly. It relies on applicative parsing. In a dynamic language, or even in a monadic context in Haskell, the parser's structure might change at runtime based on the user's previous inputs. You literally wouldn't know what the parser is expecting next until you actually execute the program up to that exact point.
Oh, I see. So you're saying that if the library allowed for dynamic runtime evaluation of the arguments, it would be impossible to predict the full set of valid inputs without actually running the binary with a partial command.
You nailed it. But because optparse-applicative enforces an applicative structure, the grammar of the command line arguments is entirely static. The library can analyze the complete map of every possible flag, option, and argument at compile time.
Without ever executing the application's core logic.
Right. But to perform that static analysis, the developer must provide an explicit, unambiguous blueprint of the arguments. The library point-blank refuses to infer the structure. It forces you to declare it.
Which brings us to the actual code fix Ang implemented, and it is deceptively brief. Ang shares the code diff, and it just consists of defining the parser explicitly. The type signature reads argparser ;parser args.
Yep.
And then the function definition right below it just reads argparser equals args. That's the entire fix. Just binding the data constructor args to the parser definition.
It looks like pure boilerplate, and, in a way it is. Ang is formally declaring to the compiler, here is a dedicated parser entity that yields the args data type.
So by isolating this definition, Ang gives the library exactly what it needs.
Exactly. It provides the optparse-applicative library with the precise static blueprint. And once the library has that bounded definition, it basically possesses the complete taxonomy of the application's interface.
But declaring a parser in a Haskell file doesn't actually tell the bash shell how to handle the tab key, does it? I mean, the Haskell binary isn't running when the user is typing out the command.
Right. The shell intercepts the keystroke before the program ever launches.
So how does changing the internal Haskell code actually alter the behavior of the operating system's terminal? Because right in the Haskell code was just the trigger, right?
Exactly. And this is where we see the secondary benefit of that strict static typing we were just discussing. Because the library now has an isolated static blueprint of the entire CLI grammar, it can do something truly remarkable.
It translates it.
Yes, it translates that Haskell-defined grammar into an entirely different language. Ang doesn't just compile the program. Ang uses the compiled program to generate a shell script.
Oh, wow. Yeah, because once compiled, the XS2 ebook app can actually generate its own auto-completion script for bash. Ang used this really specific command, $XS2 ebook --bash completion script XS2 ebook.
That's brilliant.
It's wild. The application is literally writing a script for the terminal about the app. It's like a new employee writing their own instruction manual and handing it to their boss, the bash terminal, so the boss knows how to ask them questions.
That is a phenomenal analogy. The mechanism here is just a beautiful example of code as data. The application isn't running its primary routine to convert an XS file to an ebook. It's running a metaprogramming routine.
Right.
It takes the abstract syntax tree of its own argument parser and serializes it out as an executable bash script. Bash doesn't know what Haskell is, and it frankly doesn't care. It only understands its own internal completion API.
And that --bash completion script flag bridges the gap.
Exactly, by outputting a highly specialized integration file.
So let's dig into that output, because Ang actually provides the generated bash script in the notes, and it's mechanically dense, like really dense.
Oh yeah, it has to be.
It starts by creating a function specifically for the application, _x2 ebook parenthesis. By declaring this function, the script is staking out a dedicated namespace in the shell's memory, right?
Right. Isolating the autocomplete logic so it doesn't collide with the rules for Git or Docker or whatever else you have installed.
And inside that namespace, it sets some local variables. Like one of the first things it does is declare local ifs equals $quote \n quote. What's happening there?
So ifs stands for internal field separator. The bash shell usually uses spaces to determine where one argument ends and the next begins.
Oh, right. But file names constantly break this rule. Because if I have a file named like chapter1.txt with the space in it, and the shell evaluates that using a space as the delimiter, it's going to completely tear the string in half.
Exactly. It will pass chapter as one argument and one.txt as a completely separate argument.
Which would inevitably crash the application.
Right. A good way to visualize the IFS is to think about how a CSV file works. In a comma-separated values file, the comma is the structural delimiter. But if one of your data fields actually contains a comma like a location field reading Paris, Texas, the parser will catastrophically misalign the columns unless you temporarily change the rules or escape the character.
That makes total sense. So Bash faces the exact same problem with spaces and file names.
Exactly. So by setting the local IFS strictly to a new line character, which is represented by that $ quote, backslash, end quote, the script forces Bash to ignore spaces entirely for the duration of this specific function.
Oh, so it ensures that when the script returns a list of candidate files, a space within a file name won't be misinterpreted as a structural boundary. It's temporarily rewriting the fundamental parsing rules of the shell just to safely transport strings that might contain spaces.
Yes, exactly. But, the script still needs to know what the users actually typed before they hit TB.
Right, which brings us to the next part. It tracks the index with this line. CMD line equals parenthesis dash 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 completion dash index $ KMP underscore CWord parenthesis. What exactly is KMP underscore CWord doing in the context of the shell's memory?
So CMP underscore CWord is an environmental variable injected by the GNU readline library, which is basically the underlying text input interface for Bash. When you press Tab, readline essentially issues a hardware-level interrupt.
A hardware-level interrupt.
Yeah, it pauses whatever's happening, takes a snapshot of the current command line buffer, and passes that state to the completion function. CMP underscore CWord holds the integer index of the word that currently contains the cursor.
Ah, so it's not just passing the entire string of text, it's pinpointing the exact location of the user's cursor at the millisecond the tab key was struck.
Exactly.
Because I might have, typed out a long command, realized I missed a flag at the beginning, used the arrow keys to navigate back to the middle of the string, started typing, and then hit tab.
Right, the script needs to know that it should be auto-completing the third argument, not the seventh.
That is some serious mechanical precision. So the bash script takes that cursor index, along with the contents of the command line, and passes them back to the x2 ebook executable.
Yes, and then the executable reads its static parser map, calculates the valid options for that specific cursor position, and returns the results to the bash function.
Which then feeds those results back into the readline buffer.
And suddenly, the rest of your file name appears on the screen.
Magic. Which leads us to the final critical command targeting file names in the generated script. Complete -o file names -f underscore xs2 book, xs2 ebook.
This is the actual registration hook, right?
It is the binding contract. Up until this line, we've just been defining a function and setting variables in isolation. This complete command is the moment the script actively modifies the operating system's behavior.
Because complete is a bash built-in command.
Right. And by passing the -f underscore xs2 book flag, it tells the shell, whenever you need completion candidates, execute this specific function. And what about the -of file names part?
That is particularly vital. It instructs the shell that the output from this function should be treated specifically as file paths. So this allows the shell to apply its own native file handling behaviors.
Like appending a / if the autocomplete resolves to a directory.
Exactly, or applying specific syntax highlighting if your terminal supports it. And finally, the target word xs2 book at the very end tells Bash to trigger this entire chain of logic strictly when the user invokes this specific application.
Looking at this complex generated script really reveals just how much work goes into a single press of the TB key. Managing internal field separators, intercepting readline interrupts, tracking cursor indices, registering shell hooks. It highlights the massive disparity between the user's perception of a feature and the developer's reality.
Oh, completely. From the user's perspective, TB completion is just a monolithic, fundamental property of the terminal. It's like air. It just exists.
Right. But from Ang's perspective, providing that air required diving into the Haskell source code, isolating a parser definition, invoking a metaprogramming generation tool, and wiring up a highly specific sequence of OS-level overrides. Which brings us to the overarching lesson Ang learned from this whole process.
Yes, the CLI philosophy.
Exactly. Ang's concluding thought is a direct quote. Such features should be the essential for any CLI library, especially those part of the standard library, till the next post. Yours truly, Ang. So what does this all mean? When you think about your own daily tools, Ang is pointing out a massive expectation gap here between what a developer wants to build and what the foundational libraries provide.
Yeah, if we connect this to the bigger picture, Ang's conclusion is incredibly important. When a feature like auto-completion requires manual generation and specialized bash scripts, it creates massive friction.
It does.
Ang is arguing that CLI standard libraries need to evolve to treat these user experience features as foundational, not optional add-ons. You shouldn't have to manually jump through all these hoops just to get the basic UX right.
But wait, I see the appeal of that argument. But isn't there a risk in having standard libraries do too much? I mean, if a standard library automatically injects shell completion hooks for every binary it compiles, you introduce a lot of overhead.
That's true.
You risk muddying the language's core functionality with operating system-specific edge cases, right? A standard library needs to be pristine. If you bake bash completion into the core, what happens when a user runs the binary in Zech or Fish or PowerShell?
Then the library maintainers suddenly have to support the idiosyncrasies of every shell environment on Earth. Yeah, that is the perpetual trade-off in systems design.
Right.
If you push the responsibility down into the standard library, you bloat the foundational tooling. But if you push the responsibility up to the application developer, you guarantee a fragmented ecosystem where half the tools lack basic usability features, just because the developer didn't have the time to learn bash scripting mechanics.
Exactly. So how do we fix it?
Well, what makes Ang's specific solution so compelling is that the Haskell implementation actually bypasses this false dichotomy.
How so? Because Ang still had to manually run the generation command. It wasn't completely automatic.
It wasn't automatic, but it was virtually free. This is the real magic here. Writing explicit, strictly typed code doesn't just prevent runtime bugs, it creates secondary artifacts for free. Because Haskell's type system forced Ang to be mathematically rigorous and explicit about the arg parser, the optparse-applicative library was able to leverage that strictness to programmatically generate the bash integration.
Oh, wow. I see what you mean. Ang didn't have to write a single line of bash.
Not one line. Ang only had to write correct Haskell. The architecture of the language allowed the tooling to bridge the gap automatically.
That is a phenomenal insight. The boilerplate wasn't just bureaucracy to satisfy the compiler, it was the foundation that allowed the compiler to write the shell integration on Ang's behalf.
Exactly. When the underlying structure is sound, the necessary integrations can be derived mathematically rather than crafted manually.
It shifts the paradigm from writing integrations to generating them. Well, just to recap our journey today, we started with the visceral, universal frustration of mashing a stubborn TB key on a TXT file and getting absolutely no response.
The worst feeling.
Seriously. And from there, we traced that UI failure through the optparse-applicative Haskell fix, where explicitly defining the parser unlocked the ability to generate a deeply complex bash completion script. We saw how it managed internal field separators and readline cursor indices just to safely pass a file name back to the terminal.
It's a remarkable journey from a micro-interaction to a macro-architectural philosophy, and it leaves us with an important question to consider about the broader ecosystem of software development.
Which is?
If explicit declarative code structures can automatically generate complex integrations like shell completion, what other essential user experiences are we currently building by hand that could be entirely automated if we were simply more rigorous about defining our initial blueprints?
Oh, that is such a great point. If developers like Ang have to manually jump through these intricate hoops just to get the TB key to work, you have to wonder what other standard user experiences are currently being neglected simply because developers are having to do all the heavy lifting themselves.
Exactly.
The next time you hit the TB key and the system flawlessly completes your thought, take a second to appreciate the static analysis, the metaprogramming, and the invisible shell scripts executing in the background to make that magic happen. Thank you so much for joining us on this deep dive into the hidden machinery of the tools you use every day, and remember to keep questioning the systems beneath your fingertips.